please.
Okay, sir. Thank you.
Recording in progress.
Sir, each session record होजी.
अच्छा.
Again, sir.
Madam, please start.
Okay, sir. Good afternoon, dear participant. Welcome to the first session of the third day of the ongoing FDP. The today's session is Professor R. Rabindra Kishore Mishra sir, who will deliver the talk on the meta-electromagnetics. Professor Rabindra Kishore Mishra was born in the year 1963. He was a professor in the Electronic Science Department of the Barampur University. His research extensively in the area of planar antennas and application of shock computing techniques to analysis and design of planar antennas. He was visited the University of Birmingham as a British Commonwealth Fellow during 1999 to 2000. He has supervised 24 doctoral theses. He has published 2 monographs and more than 150 law articles in reputed journals and proceedings of conference and seminar, etc. These publications have earned the IETE Sir J.C. Bose Best Application Article Award in 1999 and Sri Hari Om Ashram Perit Hariballabh Das Chunilal Research Endowment Award in 2000. Saman Chandrasekhar Award in Engineering and Technology in 2008, which is the highest award by the government of Orissa. By this, again I welcome Professor Rabindra Kishore Mishra sir to this session. Thank you, sir.
Thank you, Dr.
Sir, I will.
Paingai.
Sir.
Sir, now floor is yours, sir. You can start.
Okay.
Sir.
Okay.
Sir.
Tell me first whether it is visible and am I audible?
Yes, sir. It is visible.
Okay. So, I have 2 sessions. Today is one session and tomorrow is the other session. I have divided this deliberation into 2 parts. The first part will be the theory of metaelectronics or metaelectromagnetics, and the second part, which will be tomorrow, that will be on the applications of metaelectronics or metaelectromagnetics. What I plan to do or how I plan to proceed is this way. We will briefly revisit the reflection, refraction, etc. from the electromagnetic point of view, which usually we read in the undergraduate study as well as in the postgraduate study in the course electrodynamics or electromagnetics. So that will be a very brief discussion or recapturing. Then the theory also we will discuss. That also will be brief. Some of the steps will be detailed. Otherwise, the steps I will skip, which is easy to derive. So those steps I will skip in the theory. And the theory will be mostly based on rigorous mathematics, and applications will be definitely on antennas. So these are the two things that I am going to do. So let me start with the theory. For the theory, both for the theory and applications, we have taken some works, reported works. One is for the theory, I will take from the Capasso and his group on optical metasurface. Their work I will take. Then from Fermat, E. Fermat by Professor Raj Mitra. So these two I will take for theory. Besides normal electromagnetics that we teach in the classroom. Then for applications, we will discuss uh, some of the work done by our group while I was at Parampur University. So this is about the sources. Now let us start the theory. So to start with, I will try to give an overview of classification of materials in electromagnetics. Now, a brief overview. Now, in electromagnetics, the electromagnetic wave propagates. Electromagnetic wave contains two fields, intermingled fields, interdependent fields, electric field and magnetic field. Their spatial dependence is of the form exponential I or j into n omega by c z, if assuming that it is propagating in the z direction. Otherwise, z we can replace by r. Now let us consider a particular direction, z direction. So this is the spatial variation of either electric field or magnetic field. The amplitude will be different for both of them, but this is the variation part is this. Now in this, omega is angular frequency, c is the speed of light in free space, n is important, n is the refractive index. How do you find the refractive index? It is square root of epsilon and mu, that is permittivity and permeability, take their product, take the square root. Now when you take the square root of anything can be either plus or minus. Like if you take 4, square root of 4 is plus minus 2. Therefore, n or the refractive index is equal to plus minus square root of epsilon into mu or permittivity into permeability. Now, how does this affect the material, or how do we use this for classifying material? Let us see that. Now, as we saw, square root refractive index n is equal to plus minus root over of mu epsilon. Therefore, maybe mu and epsilon can be positive or negative. So if they can be positive and negative, then if we draw x-axis and y-axis, in the x-axis we take epsilon, y-axis we take mu, then the whole plane will be divided into 4 quadrants. In the first quadrant, epsilon and mu both will be greater than 0. This quadrant is usually the common quadrant that we use. The materials that we use, the dielectrics that we use in this quadrant are most common, like water, crystal, semiconductors, etc. are in this quadrant. The beauty of this quadrant is the wave vector k. Wave vector k is perpendicular to E and H. If you take E electric field, H magnetic field, and K the wave vector, they form a triangle. So they are perpendicular to each other. So K is perpendicular to E and H. Similarly, the Poynting vector S is also perpendicular to E and H. E cross H gives you HS. K and S both are in the same direction. Both are vectors, both are in the same direction in this quadrant. The first quadrant, K and S are in the same direction. If we come to the second quadrant, next. In this second quadrant, mu remains positive or permeability remains positive, but permittivity is negative. Now, the moment permittivity becomes negative, what will happen? Square root of epsilon mu. So that part will become imaginary. So n or the refractive index will become imaginary. E and H they vary as exponential I into n into omega by cz. N is imaginary, which means n is equal to in. So in into I is minus n. So E and H will start decaying, exponentially decaying. So these were the waves in the second quadrant are evanescent waves. Where you find evanescent wave? Usually we find evanescent wave in metals. Electromagnetic wave is evanescent in metals. In metals, epsilon is negative. And naturally occurring metal, epsilon is negative. There we find evanescent wave. As you penetrate into metal, the field dies down. Now come to the third quadrant. In the third quadrant, both epsilon and mu are negative. So square root of minus epsilon minus mu, which is plus epsilon mu. So n will be either plus or minus. Usually n is taken to be negative in this quadrant. We will see why it is taken to be negative. Under what condition it will be negative, that we will see shortly, but it is usually negative. Now if n becomes negative, but it is propagating. So there is no change in propagation. So it will be propagating because n is negative, the Poynting vector and the propagation vector k, S and k are anti-parallel to each other. They are parallel but in opposite directions. That is the beauty of this quadrant, the third quadrant. So our discussion will be mostly about this third quadrant in the beginning, then we'll leave this out. So in this quadrant, epsilon is negative, mu is negative. Then comes the fourth quadrant. In the fourth quadrant, mu is negative, epsilon is positive, so it behaves similar to the second quadrant. There will be evanescent wave. This is called, if mu is negative, it is called magnetic plasma. This does not occur naturally, neither at optical wavelength nor at electromagnetic wavelength. Similarly, electric plasma occurs naturally at optical wavelength as well as electromagnetic wavelength. So this is the division of or a classification of electromagnetic materials. They can be common transparent dielectrics or electric plasma or negative index material or magnetic plasma, depending on what value we are taking for epsilon and mu. Next. Based on this, the material that occurs in the third quadrant, these are called metamaterials. You know, any material, if you consider any material, the material consists of atoms. So many atoms constitute the material. So natural materials, they have their atoms, original atoms. Now, what is metamaterial? Meta means beyond. In Greek, meta is a Greek word which means beyond. So beyond naturally occurring material, any material which is beyond naturally occurring material, which means Any material which is engineered or designed artificially, these are called metamaterials. Next. By definition, how do you realize metamaterial? It is an arrangement of artificial structures or artificial structural elements which are designed to achieve required advantages and their electromagnetic properties are unusual. So what is unusual electromagnetic property, that we will see how do you get this by artificially structured atoms. So these artificial structural elements, these are considered as atoms for the metamaterial. By properly arranging them with proper periodicity, we get the metamaterial for required electromagnetic property. So, which is not usual, the electromagnetic property is not usual or not natural, unnatural electromagnetic property. Next. Now, electromagnetic material or optical materials, both are physical band gap materials are similar to electromagnetic material. PBG is physical band gap materials. These are, let us compare these with metamaterials. For comparison, what we do is we take the ratio of the dimension of the atom with the wavelength. Atom is the atom that constitute the material. So the structure, basic structure that constitute that material, basic structure, which are arranged periodically to constitute the material. So we take the dimension of that matter or that structure, which is A. So A by lambda. If A by lambda approaches infinity, which is A is very large compared to lambda, then those materials and they follow the geometrical optics and ray tracing. So their properties, they follow geometrical optics, ray tracing, etc. For example, lens system, shadows that we see, these are all based on these materials. On the other hand, if they are almost equal size, so size of the material equals the wavelength, then the structure is dominating. When the structure dominates, then the properties are determined by diffraction and interference, which is the wave optics. And the first part, A greater than lambda, it is geometrical optics. Here it is wave optics. When A is approximately equal to lambda, wave optics. For example, photonic crystals, phase array radars, X-ray diffraction optics, etc. Then the extreme case, other extreme case is A is much less than lambda, sub-wavelength size. Then the effective medium description is given by only Maxwell's equations with varying mu, epsilon, n, z, permeability, permittivity, refractive index, and characteristics impedance. These are optical crystals, metamaterials, etc. They come under this category. So this is another way of classifying materials. Next. Now, what is the speciality of metamaterial? Look at the two figures on the left hand side. In the top figure, what we are seeing is an incident ray from the third quadrant. It gets reflected and a part of it gets transmitted. Reflection is in the second quadrant if the incident is in the third quadrant, and the transmission is in the first quadrant. Here remember, both the sides, left side and right side, are having positive n, positive refractive index. Look at the figure below, bottom figure. Same incident ray in the third quadrant, reflection occurs in the second quadrant, but refraction or transmission occurs in the fourth quadrant. So this is called negative refraction. Instead of first quadrant, it comes to the fourth quadrant as if it is getting reflected in the bottom part of this figure. So that type of transmission is called negative refraction. For this to occur in the first medium, the n should be greater than 0. In the second medium, n should be less than 0. N should be negative in the second medium. Now, how to ensure n to be negative? We know epsilon can have a real and imaginary part, mu also can have a real and imaginary part. Then refraction in the refractive index n, and to find that what we do is we first find n square. N square is equal to epsilon into mu. That will be a complex number. So n is equal to plus minus root over of epsilon mu. That again will be a complex number n dash plus a n double dash. Then we define figure of merit for this material as F is equal to absolute of n dash divided by n double dash. Now, once we know this n, then we say the n is negative or the refractive index is negative if it follows this condition. Condition is epsilon dash into absolute of mu double dash plus mu dash into absolute of epsilon double dash is less than 0. If that happens, then we categorize n to be negative for that material and we call that material as the metamaterial. Next. Now, these are some pioneers of the negative index materials or metamaterials. It started with Schuster, who said energy can be carried forward at the group velocity but in a direction that is antiparallel to phase velocity, that we saw in the third quadrant. K and S are antiparallel to each other. The negative refraction and backward propagation of waves was proposed in 1945 in a book by Mandelstam. Then came the pioneering work of Maslego in 68, who studied the left-handed material when what will happen to electromagnetic properties when both epsilon and mu are negative. Then Penry realized negative mu. Negative epsilon is metal, but getting negative mu was difficult. Penry realized that. So he realized that, then he designed a perfect lens, then he designed a EM cloaking, etc. So that way the research started uh, progressing. Next. Now, what is the advantage of this getting negative refraction, etc.? First thing is, take a coordinate system, draw a line. In the coordinate system, find out the points in the coordinate system through which the line is passing. So that line is the ray of light. It is XY coordinate system, Cartesian coordinate system. Then distort the coordinate system. Then the line will also get distorted because it is run on this plane. So if you distort the plane, line will play distorted, which means the propagating ray, propagating electromagnetic wave is also getting distorted. The path is getting distorted, which means the trajectory of any ray of light or electromagnetic wave will get distorted in a distorted coordinate system. So to get a distorted coordinate system from XYZ to UVW, we require a transformation. A transformation in coordinate system is equivalent to a refractive index change in refractive index. Why? As you know, if you take two oh, materials with different refractive indexes or different refractive indices, then as light propagates, electromagnetic wave propagates from one medium to other medium, it will change its direction, path. So change in refractive index result in change in path, or vice versa, change in path requires change in refractive index. Therefore, what we have to do, we have to use the transformation theory to calculate the refractive index for finding out the distorted uh, ray trajectory. So once you fix the ray trajectory, then to follow that ray trajectory, what will be the refractive index? That we have to find out using the transformation theory. The equation that we use is N dash. N dash is the new refractive index that is equal to N into G. G is the transformation of the coordinate system. So that is obtained from coordinate transformation. Next. Now, among all these, as we said, when the size is very small, size of the object, size of the unit chain is very small, we have to use Maxwell's equation. Now, what are Maxwell's equations? These are nothing but these are extension of Faraday's principles of lines, electromagnetic lines of forces. So Faraday mostly thought about B. Maxwell have thought about D from his from previous knowledge, whatever previously was existing about D. So these are the four equations, Maxwell and Faraday equation. We call it Maxwell-Faraday equation. Generally, people call it Maxwell equation, but that is not fair to Faraday because the first equation Maxwell got from the Faraday's experiment. So, and to be fair, we call it Maxwell and Faraday equation, these four equations. They have a beauty. Next. The beauty of this is it has a curious property. Take two coordinate systems, Cartesian coordinate system, write the Maxwell's equation in component forms, then take any arbitrary coordinate system, write the Maxwell's equation in component forms. The component forms in both the coordinate systems are same. What is different is the field becomes different, new field, new value. So H becomes S dash, D becomes D dash. Then important thing is mu becomes mu dash and epsilon becomes epsilon dash. So from the form of Maxwell's equation remains same in any coordinate system, only change is in mu and epsilon. Next. These theories, etc., regarding the metamaterial, they started with the formulation of FDDD. So look at the top and bottom figures. Top figure is using Cartesian coordinate system, Cartesian geometry. The same principle can be applied when you use cylindrical geometry like optical fiber modeling. Simply what you do is when you come from the top to bottom, change the value of epsilon and mu in the calculation. It started with finite difference time domain calculations. Next. The steps that we require to follow in these cases are start with a coordinate transform. So XYZ is your Cartesian coordinate system. Transform it to Q1, Q2, Q3. So Q1 will be dependent on XYZ, Q2, Q3 also will be dependent on XYZ. So make a coordinate transform. Then rewrite the Maxwell's equations in the new coordinate system. Remember, the form of Maxwell's equations will not change in the new coordinate system. Form will remain same. So you will write as curl of E tilde. E tilde is the electric field in the new coordinate system that will be equal to minus mu tilde. Mu tilde is the new mu value in the new coordinate system. Mu tilde, mu 0, dou H tilde by dou T. Similarly, curl of H tilde. Then we calculate the new value of epsilon mu following this equation. Epsilon tilde will be epsilon I Q1, Q2, Q3 by Q1, Qi square. Similarly, mu I tilde will be Q1, Q2, Q3 by Qi square into mu I. So original value into this. What is this Qi? Qi is dou x by dou Qi square plus dou y by dou Qi square plus dou z by dou Qi square. And what is the new electric field in the coordinate system? E tilde is Qi into Ei. Similarly, Hi tilde is Qi into Hi. So this was given by Pendry and his co-worker Ward. From this, what we now find is Maxwell's equation can be transformed into new geometries where the surfaces are curved or it has a new form of coordinates, but we must change epsilon and mu. Next. Now, this is about meta material. Then we come to the topic that we are going to discuss today, which is the meta surface. Next. Now, before coming to meta surface, there are three things that we should know. One is called frequency selective surface, FSS. It has excellent filtering and polarization property. It can You can reduce dimensionality. Dimensionality is reduced here, 3 to 2 dimension. Metamaterials are 3-dimensional. These are 2-dimensional, so reduced dimensional property. But these are being passive mostly. Their signal processing is limited. By design, their signal processing is limited. So you cannot incorporate into the design of the uh, surface the signal processing. Similarly, uniformity is a restriction. The surface has to be uniform. That is a restriction. Then we have metamaterials. In the metamaterials, beauty is we have extra field control. So E and H, etc., we can control it. We have signal processing part embedded into it, but these are bulky, 3-dimensional things, very lossy, and it is difficult to fabricate because these are 3-dimensional things. So small structure, 3-dimensional fabrication becomes difficult. Even itself fabrication becomes difficult. Ultimately, realization of metamaterial becomes difficult under different situations. For different applications, the fabrication becomes difficult. So it becomes mostly impracticable in most cases. But when we come to the meta surface, next, you have extra field control here. Extensive processing, signal processing is available. Reduced dimensionality because these are two-dimensional. So and they have small profile being two-dimensional. Low loss because these are 2D elements, so only loss is in one plane, so low loss. And since these are 2D, so fabrication is easy. So all the requirements are met in the meta surface. So we go for meta surface rather than meta materials nowadays. Next. This meta surface, using meta surface, what we do is instead of providing negative permeability or negative permittivity or negative refractive index, we change the wavefront. Why we were using negative permittivity or negative permeability or negative refractive index? To change the direction of the electromagnetic wave. It was the refraction was in the first quadrant. If incident is in third quadrant, that we were taking to the fourth quadrant. Now, instead of using metamaterials, using the negative refractive index, if we can do that the same thing, then it is advantageous if you use a two-dimensional structure. So how you will do this? By changing the wavefront. So this is called wavefront technology. This is an alternative and transformation electromagnetics. From that we got the lesson that it has beautiful physics, but it is very limited technology penetration because of the fabrication complexity. Unlike the transformation electromagnetism, which is metamaterial, the spatial confinement is not the principle. Spatial confinement of the electromagnetic field is not the principle here. Here the principle is wavefront management. Refractive index is not the useful quantity here. What is the useful quantity here? Change the local phase and amplitude to control the electromagnetic field. So along the surface on which we are designing the metamaterial on the surface, we use sub-wavelength antennas to change the phase and amplitude. Next. This is actually based on the principle of least action. Principle of least action was given by Maupertuis, who felt he was a philosopher who felt that nature is thrifty in all its action. That means nature is lazy. It tries uh, not to work, to do minimum work for anything. For a job, the work should be minimum. That is what he said. That was given in mathematical form by Euler. As the work or the action delta S0 is equal to delta integration from A to B. When you are moving an object or a point from A to B, P dot dq, P being the momentum and q being the path along which it is going. That should be equal to 0. That is what is given by Euler. Then, using wave particle dualism, de Broglie gave the final uh, answer as the Fermat's principle, or which we know as the principle of least action, which is delta integration A to B dl dot n is equal to 0. K, P is equal to h cross k, so put that P is equal to h cross k, h cross is not 0. So then keep k, from that you get this value. Next. So that was one principle. The other principle comes from the uh, famous French mathematician Emma Noether. She was a very famous French mathematician and perhaps the only lady mathematician in the early days of mathematics. She said that if any physical in the physical space, the space is continuous and has smooth symmetries, then every differentiable symmetry of the physical action or a physical system has a corresponding conservation law. Conservation laws, he associated that with symmetry. For example, if you have translational symmetry, that is associated with conservation of momentum. Similarly, if you have temporal symmetry, symmetry in time, that is associated with conservation of energy. Similarly, there is a list of 41 symmetries that she found out. So these are two important things that we use in metasurface, particularly when we design these vortex beams that maybe you will see in the next class, next lecture. Next. So these are the two basic principles. Now, we will allow or use those principles in the existing physics laws of electromagnetics. The first law that comes to my mind is the Snell's law or Descartes' law. Both of them give the same law. This law is next law of reflection and law of refraction. Sin theta r minus sin theta is equal to 0, which is law of reflection, from which we get theta r is equal to theta I. Similarly, nt sin theta t minus ni sin theta I is equal to 0, or sin theta ty sin theta I is equal to ni by nt. This is the law of refraction. Then the main law is incident, reflected, and transmitted rays and the normal to the interface, they lie in the same plane. Now, how do they got this? They got this using the principle of restriction. Next. I'm using the principle of restriction in which the momenta difference between blue and red path that is shown below is 0. So, conservation of momentum, Noether's theorem. So, two things you have seen together. Now, the Noether's theorem and the principle of restriction. Both these come into play in establishing the Snell's-Descartes law. Next. Now, I will come to a brief discussion of electromagnetic theory on the Snell's law. So when we study this in the undergraduate or postgraduate course, we look at the Snell's law from electromagnetic theory. Now here you see on the right hand side, we have two medias. In the medium 1, we have K1, the propagation vector is K1. In the medium 2, propagation vector is K2. In medium 1, omega 1 is the frequency. In medium 2, omega 2 is the frequency. As you know, if it changes the medium, the frequency does not change. So omega 1 is equal to omega 2. Then at the interface, we should have the continuity of K. Interface is also K2x should be K1x. Now K1z is the direction. If K is divided into two components, horizontal and vertical components. Vertical component is K1z and our horizontal component is K1x. So in these, and those two are given shown here. In the second medium, K2x is greater than K1x. At the interface, they are same. And the first medium, K2x is, there is no K2x. Actually, K2x may be less than K1x. Next. Now, based on that, let us say Ki is equal to that we define as K0. K0 is the wave number in free space into Ni. Ni is the refractive index of the I is for the incident wave into Ki cap. Ki cap is the propagation vector of the incident wave. Similarly, Kr and Kt. So these are given same form. Next. Then what is Ki cap? Small Ki cap. That is given by using the relationship between spherical coordinate system and Cartesian coordinate system. You get this expression for Ki. Then for Kr, next. For Kr now, you can see the last term is plus cos theta Kr. For the Kr, it is plus. For Ki, it is negative minus. Why? Because Kr is returning back, it is getting reflected. R is for reflection, it is getting reflected. When it is getting reflected, the Z component is reflected. So Z component changes the sign. Therefore, the last one is plus cos theta R. Then Kt, there is no reflection, it is transmitted next. So it is transmitted, the form is same. So Ki, Kr, Kt forms are given. Next. Now we can write from this, we can find out what are the x component, y component, and z component. How to find out the x component? Multiply with the x cap. To find the y component, multiply with the y cap. So that is what we are doing. So Kix is equal to K0 Ni and Ki dot x cap. Kiy is equal to K0 Ni Ki cap dot y cap. Similarly for R and T. Next. So this we can write in a compact form as KIRT. So it can be either I or R or T. For any of these, the form will be equal to K0 in IRT, I or R or T into, we are finding the x component. So for the x component, multiply with the x cap, Ki multiply with the x cap, only first term will be there. Sin theta I cos phi I. Similarly, Kr sin phi A, sin theta R cos phi R. Kt sin theta T cos phi T. So accordingly, this is written sin theta into cos phi, then IRT will be subscript. Similarly, next. KIRTY, same procedure, so the second term will be there. Sin theta cos phi will be there. IRT will be there. So these are the equations. Next. Now these two, we have seen the compact forms are these two. Now let us find out the Snell's law using this. Look at this figure. In this figure, we have incident wave P, reflected wave R, transmitted wave Q, incident angle theta I, reflected angle theta, and a transmitted angle theta T. Interface normally you can see. In the first medium, it is N1, N is N1. Second medium, N is N2. Velocity is V1 in the first medium. second medium it is V2. Next. This we know Ki dot R is equal to Kr dot R is equal to Kt dot R at the interface because of the boundary condition. Next. So Ki dot R is Kix dx plus Kiy dy. So that is equal to Kr dot R, which is Krx dx plus Kry dy. Similarly, Kix dx plus Kiy dy will be Ktx dx plus Kty dy. Now equate the equal components, same component, dx component, dy components, etc. If we do that, if we equate Kix is equal to Krx, that will be Ktx, Kiy will be Kry, Ky by equating the same terms. Next. Then in the one-dimensional case, if this is for the three-dimensional case, for the one-dimensional case, put for Kix and Kix, Krx values given in the red in the above. Put those values, from that you will get sin theta I by sin theta t is equal to mt by ni. This we have done while we are studying electromagnetics in the undergraduate and postgraduate level. Similarly, theta r is equal to theta I, phi r is equal to phi I, phi t is equal to phi I. What is theta r and theta I that you see? It is the angle between normal and the incident angle ray in the plane of incident. If we have a perpendicular plane to the plane of incident, in that plane, these are phi r, phi I, and phi t. Next. Now let me ask you a question, hypothetical question. Suppose we have a spatial distribution of different phase discontinuities along the entire interface between two different media. We have two media separated by an interface. Along the interface, there is a phase discontinuity continuously. What will happen in that case? The hint to the answer of this is the wave propagation will occur with phase discontinuities. Wherever there is a phase discontinuity, there will be a different wave. So how it will be different? See, next. Look at this. The orange line, straight vertical orange line shows you a discontinuity point. To the left of that orange line, it is a sine omega t minus kxx. To the right of that orange line, it is a sine omega t minus ksx plus the change in the phase phi jump. Phi jump is so any number of discontinuity will keep on adding that much of phase change. So in the waveform, there will be continuous phase change. Continuous phase change will result in distorted wavefronts that we'll see shortly. Next. Now this shows you what I told you earlier, theta I and phi I, theta r and phi r, theta t and phi t, etc. That is what is shown here. This try to remember this or visualize this. I have already supplied the material. You can refer this figure from that material for further studies. We have two planes. One is plane of incident, other is the vertically changing or intersecting it. The other plane which is horizontal, vertically intersecting it, or which is orthogonal to it or perpendicular to it. Then we have a horizontal plane. Horizontal plane is the plane of interface. Then this on the two vertical planes, one of them is the plane of incidence, other is the plane which is perpendicular to the plane of incidence. Next. Now we'll consider what happens when we have spatial phase gradient. We can have two things. We can have reflection, we can have transmission at the interface between two media. We will have reflection or transmission. For reflection, we will have Ki dot r, that we know Ki dot r is equal to Kr dot r when the phase difference is not there. If there is phase difference, we will add phase difference to this. So Ki dot R plus delta phi R is equal to Kr dot R for reflection. Similarly, next. So if I similarly by expanding this, I will get Kix dx plus Kiy dy plus delta phi r is a function of xy that is equal to Krx dx plus Kry dy. Next. And now from that, what we get Kix is equal to Krx when the delta phi is 0, Kiy is equal to Kry when delta phi is equal to 0. But if there is a phase gradient, Kix plus dou x phi r is equal to Krx. What is dou x? That is partial differentiation with respect to x. So dou x phi r means partial differentiation of phi r with respect to x. Remember this. Similarly, Kiy plus dou y phi r is equal to Kry. Dou y phi r is partial differentiation of phi r with y. So this happens for reflection. Now for transmission, next Ki dot r plus delta phi t r will be ktr, similar as the reflection. So I'm not describing this. So finally, you will get kix plus and dou x phi t is equal to ktx, kiy plus dou y phi t is equal to kty. From this, we will get the equation, general equation for transmission and reflection. Now, and look at this figure. This gives you if the phase profile changes, what happens to the amplitude, how the wave is getting changed. So the with phase profile is in the x-axis, y-axis gives you the amplitude 0 to 3. How it keeps on changing with change in phase profile, or if you give a spatial phase gradient, how the electric field will keep on changing, how the direction will keep on moving. Next. So now we'll continue with what we discussed up to now. Now KT, from this from the previous discussion, we can find out what is KT. KT is the transmitted um, wave vector. So KT is equal to Ki minus n cap Ki cap dot n cap plus n cap kt cap dot n cap. Kt cap dot n cap is scalar that multiplied by vector n cap. Similarly, ki cap dot n cap is a scalar multiplied by n cap. So right hand side is completely vector. So this one, if I expand it, n cap for ki cap, we can write k0. Ki cap is k0 into ni into small k cap, which is the wave vector. That into n cap minus similarly n cap k0 nt into k0 into nt into k cap dot n cap. Now k cap kt cap dot n cap, that is uh, a dot b is ab cos theta. So from that you get this cos theta t, angle between the normal and the transmitted wave. That angle is theta t. So that is cos theta t. Next. Now from cos theta t we can write as cos theta t is equal to root over of 1 minus sine square theta t. So for sine square theta t, we can write it in terms of, because sine theta I and cos theta I are related by Snell's law. So for that we can write sine theta I and I by nt for sine theta t. So if we put that, then the last part is root over of 1 minus sine theta I and I by nt square. Now multiply, take nt within the square root. Next. So that gives you this last part is root over n cap k0 nt into root over of 1 minus sine theta I. Sine theta I you can write as you know, a cross b is ab sine theta. So for sine theta I we write ki cap cross n cap. So that gives you sine theta I. Now take n cap inside nt inside the square root. Next. So kt ultimately becomes ki minus n cap k0 that I have taken common n cap k0 from the last two terms. Take n0 k cap n cap k0 common. So ni ki k cap dot n cap plus root over of nt square. Nt we have taken inside the square root, so it becomes 1 into nt square, that is nt square, minus ni I into uh, ki cap cross n cap. What happens to nt? Nt is cancelled with nt square. Nt square is in the denominator, nt square is multiplied with that, so that cancelled now. Next. So that equation I have taken, the last equation is on the top. Next. So kix plus tau phi x is equal to krx. For the reflection, this we have already seen. Kiy plus dou phi y dou y phi r is equal to kry. This we have seen for reflection when we add the phase gradient along the surface. Similarly, for transmission, we have seen the equation. These two equations we have seen. From this, what we'll get is krj. Uh, krz is equal to kij minus 2k0 ni z cap into ki dot z cap. This is for the z component of the reflected wave. XY component we have seen, but for the Z component, we don't have a phase gradient. Remember this, we don't have a phase gradient, but only reflection in there. So for the Z component, we don't have a interface, separate interface. At a point, this is getting reflected. So Kiz minus what is getting reflected. So that part is 2k0 ni z cap into ki dot z cap. Next. So Kr, ultimately from this, we will get Kr is equal to, add these three components, Kix, Kiy, Krz. So Krx, Kry, and Krz. If you add these three components, that ultimately gives you gradient of delta phi r plus Ki. Ki comes from Kix plus Kiy, uh, Kiy plus Kij, that gives you Ki, minus the last term to K0, Ni, N cap, Ki, Z cap. So Krz we have got. For the reflected ray, the reflected wave vector we got. Next. Similarly, KTZ, again, that will be similar to KRZ. This will be KTZ, we have already found out that is the expression in the top, that expression we have written. And remember that when this happens, delta Z or dou Z of delta phi t is equal to 0. There is no change of delta phi t. There is no change, no phase gradient along the Z. So dou Z of delta phi t is equal to 0. Using this, we get next kt in the form of total kt, not the Z component. Total kt form is delta of del of delta phi t plus ki minus n cap k0 into this. So this form we get. So kr and kt, these forms, when we have a phase gradient along the interface, kr and kt forms we have got. Next. Now we'll get the look at the generalized Snell's law from this kr and kt. Kr expression is in the top, kt expression is in the second line. Now, what happens if these are the equations in the three-dimensional case? Now, if you come down to one-dimensional case, so simplify this to one-dimensional case from the three-dimensional. So simplify this to one-dimensional case. So then we will get refraction with phase shift gradient in one dimension. Nt sin theta t minus ni sin theta I is equal to 1 by k d phi by dx. So this is in the one-dimensional case. This is called the generalized Snell's law. Nt sin theta t minus ni sin theta I is equal to 1 by k d phi by dx. Left hand side we understand. Right hand side was earlier 0 when phi was 0. There was no phase gradient. This was the right hand side was 0. Now, when there is a phase gradient, then this will be 1 by k d phi by dx. What does this mean? This means that the phase gradient, if you include a phase gradient, that will affect the ray direction. So you can control the ray direction using the gradient of phase. So to control the ray direction, we require a gradient phase shift. Or if we have a gradient phase shift, that will change the ray direction automatically. That will change the ray direction. So as sin theta t by sin theta I will not be equal to ni by nt. It will be ni by nt into 1 by k into and dou pi by dx, something like that. Next, next. So we'll continue with that. So we have got these two equations for the reflection. Now for the reflection, same principle, same thing will apply. So sin theta r minus sin theta I, that will be equal to 1 by k and d phi by dx. Next. You see what happens if you keep on changing x in the along the x, there is a phase gradient. So theta r is changing from 1, it is changing gradually. So when there is no phase change, it is 1 sin theta r is equal to, or theta r is equal to theta I. Then if you keep on changing, the theta r keeps on changing. It does not remain theta r, does not remain theta r. Next. Similarly, and this is the equation, the 3D equation for transmission, law of transmission. This is the 1D equation for law of transmission. Similar phase shift for normal incidence. You can see how it is changing. Theta t is changing. When next. Now this shows, this I am not going to discuss. This only shows that uh, of the incident ray, reflected ray, and the normal to the interface, they are not in the same plane. This from this figure you can see, based on the phase gradient. If the phase gradient is only along the x-axis, then they may be in the same phase. But phase gradient is in the along the x-axis as well as along the y-axis on the plane of in a interface, then they will not be in the same phase. So out of plane reflection and refraction are possible using phase gradients on the plane separating the two mediums. Next. Now, what happens to reflection and transmission generally, in general, from what we have discussed up to now? What happens to reflection and transmission? We have an incidence wave. If we have an incidence wave, that will get reflected at the interface. Now, that interface reflection, if it gets reflected normally, it is called ordinary reflection. About 40% of the wave will get ordinarily reflected. Then there will be another reflection which is called anomalous reflection, which can be on the same side of incidence. That will be about 20%. Similarly, there will be ordinary refraction, which will be about 20%. Anomalous refraction, which will be about 10%. The remaining 10% is absorbed by the antenna, which is providing the phase difference. So this is what happens to the reflected and transmitted beams when we use a phase gradient. Next. Now, when we use a phase gradient, what happens physically? That we can see from the Huygens principle. We know wavefront is that is what is traveling. The wavefront is parallel. Now, if you consider a normal in the interface which has no phase gradient, then you incident a primary wavefront. Then every in the wavefront, look at these secondary waves. The secondary waves will be of same radius, and if you draw a normal to the wave or to the secondary phases or secondary waves, that normal will give you the direction in which it is propagating. So that you see on the left hand side. On the right hand side, it gets distorted. Why? Because the envelope of secondary waves with radius is changing. The radius is lambda by 2 pi into phi x that we have seen k0 1 by k into d phi by dx or phi change in phase. So 1 by k is lambda by 2 pi. So or 2 pi by lambda is k that you know. Lambda by 2 pi is 1 by k. And so that into phase change. So because as the phase changes means with position. Phi is changing with x. X means with position. With different positions, the phase is different. Therefore, the radius of the second wave, secondary wave is different. Since the radius of the secondary wave is different, then join the peaks of the secondary waves, the radius of the secondary waves to form a plane. That plane will be distorted. So a distorted wavefront in a different direction will propagate because of the phase changes. Next. Now let us see what happens to the critical angle. Now we know critical angle for refraction that is known to us. Now, what we'll do is, in this case, we'll consider critical angle for reflection as well as critical angle for the refraction. Now, we know ordinarily theta r is equal to theta I if there is no phase change. So, there is no phase change, uniform phase, theta r is equal to theta I. Similarly, phi r is equal to phi I. So, if theta r is equal to theta I and phi r is equal to phi I, then we know the equation, generally Snell's equation is ni sin theta I cos phi I plus 1 by k naught dou x phi r is equal to ni sin theta r cos phi r. Similarly, for the dou y component. So this we know. Next. Now from this we can find out what is phi r. Simple algebra, the trigonometric algebra, use trigonometric algebra, you will get phi r is equal to tan inverse of this quantity. Next. So from that we'll get also get theta r. What is theta r? Theta is sine inverse of this quantity, the quantity inside the bracket. Now for critical angle, what is critical angle? Critical angle is the for reflection it will be the angle. Find out the angle of incidence for which the reflected angle is 90 degree. So theta r has to be 90 degree. Theta r is to be 90 degree means sine inverse of this quantity is equal to 90 degree. Sine inverse of which quantity is 90 degree? We know sine inverse of 1 is 90 degree because sine 90 is 1. So sine inverse of 1 is 90 degree or pi by 2. So the thing which is within the bracket that is equal to 1. Next. So that part has to be 1, sine inverse of this quantity. So that quantity has to be equal to 1 for theta to be 90 degree, reflected angle to be 90 degree. So that has to be 1. If that is 1, that contains angle theta I. So solve that for theta I will be next. So theta I will be sine inverse of 1 minus 1 by ni k0 dou phi x dou x phi r for theta r is equal to 90. So this is the expression. Theta is for when incident angle is this follows this expression, then you will get theta r is equal to 90 degree. Next. Now we'll look at the critical angle for transmission or reflection. Same thing, we know the equations for when there is no phase gradient is on the left hand side. The right hand side is when we have phase gradient. Next. From that we can find out what is the phi t. Similarly, we can find out what is theta t. Now theta t, the right hand side part has to be 1 if theta t has to be 90 degree. Sine inverse of whatever is there, that has to be 1. So for that to be 1, next, theta I has to be sine inverse of nt minus 1 by ni k0 dou x phi by nt. So that will give us theta t is equal to 90 degree. So to get theta t is equal to 90 degree, theta I is this. So this is the critical angle when we have a phase gradient on the interface. Next. Then we consider what is called phased array. Phased array means we arrange antennas uh, on a surface so that from that antenna if you make or we arrange reflectors on a surface along one line, single line. So linearly we arrange reflectors or scatterers or antennas so that when we make an normal incident onto those scatterers or those antennas, then the reflected one or the antennas, whatever the antennas transmit, they will be in a direction theta t. Direction to theta t means the ray direction and the normal direction. The angle between these two will be theta t. So if you can arrange that particular thing, that is called a phased array. An array arrange it in which particular phase. So each element has a phase difference, defined predefined phase difference, so that it is getting transmitted along theta t. So how to do that? That is important. How to arrange it? How to find out what is the phase? Now we are considering normal incidence. Therefore, theta I is equal to 0 for the phase array. You can consider any other incidence. So you can take theta I accordingly. But here I am considering normal incidence. So theta I is equal to 0. This is for simplification. Now nt is equal to net transmitted and incident. Both are in the free space. Therefore, nt is equal to ni is equal to 1. Next. So if you put nt is equal to ni is equal to 1 and theta I is equal to 0 in the generalized Snell's law, then we get sine theta t is equal to 1 by k0, which is lambda 0 by 2 pi into d phi by dx. You can simplify this or directly find from this what is d phi. Next. So this is simplification. What is theta t? That you can find out the angle of theta t if d phi by dx is given to you. So this is 1 by k0 d phi by dx. So that will be theta t. If you know d phi by dx, you can find out theta t. Otherwise, if you want to find out what is phi uh, given theta t, then what we will do is next. Find out what is d phi. D phi is equal to k0 dx. D phi by dx is equal to k0 sine theta t. So d phi is equal to k0 dx sine theta t. Integrate it on the both sides. Next. If you integrate it, it gives you phi is equal to k0 x sine theta t. So phase difference, what is the phasing that you can find out? What is the angle if phase is given? Angle we can find out. If angle is given, phase is we can find out. This is the theory for phase. That is simple theory using very simplified theory. It's not actual theory is very complicated, but this is very extremely simplified theory for phase array. Next. In phase array, we considered one-dimensional distribution of the scatterers or antenna or the reflecting elements. If we consider a two-dimensional case, this is called a reflector array. For the reflector array, again, the condition that we will consider is theta r is equal to 0. So reflected rays, you incident anything onto this reflector array, the reflected ray must come out at 90 degrees. So theta r is equal to 0. Now, these two equations that we see above, these two equations are from the generalized Snell's law. In this, put theta r is equal to 0. If you put theta r is equal to 0, we get dou x phi r is equal to minus k0 sine theta I cos phi I. Dou y phi r is equal to minus k0 sine theta I sine phi I. This we get by putting these equations. Now rearrange that. That will give you dou x phi r by cos phi I is equal to minus k0 sine theta I dou y phi r by sin phi I is equal to minus k0 sin theta I. Look at the right hand side. In both the right hand sides are minus k0 sin theta I. Next. Now rearrange that. If we rearrange this, we'll get dou x phi r is equal to dou L phi r cos phi I, dou y phi r is equal to dou L phi r sin phi I, where this dou L phi r is the common factor which was the right hand side of the above equation, second equation. So next. Now you can write dou L phi r is equal to minus k0 sin theta I. So once we get this equation, then we can proceed next. Then we can proceed with what happens. So how to design or what happens. So dou phi r we know. So from that we can get d phi r is equal to minus k0 sin theta I dx. Then look at the figure. From the figure we can find out what is theta I. So theta I will be tan inverse 1 by x. So this will give us dl was a very small distance along theta I. A very small distance along the reflector ray. So if you take that d theta I by dl, or from that you will get dl is equal to h by cos square theta I d theta I. Next. So from these two equations, we will get phi theta is equal to phi 0. Phi 0 means phi at theta is equal to 0. That is what is phi 0. So phi 0 plus integration 0 to theta of minus k0 sin theta I. Also that remains as it is. Then for dx, we have found out what is dx. dx is h by cos square theta I d theta I. So put that value. Next. So if you do that, and do the integration, that will give you phi 0 cos k0 h into minus cos theta inverse integrate limit 0 to theta. So that is phi 0 minus k0 h into 1 by cos theta minus 1. Next. Also from that you take phi 0 to the left hand side. So that gives you phi theta minus phi 0, or that is phi r theta is equal to 0, that is on the left hand side, is equal to k0h minus k0h into minus 1 is k0h. Then minus k0h into 1 by cos theta is k0h by cos theta. So this is the final equation in the design. So once phi 0 is fixed, you can find out what is phi theta are depending on theta and k0 and h. Now, how to realize this? That is the most important thing, how to realize this. To realize this, what we do is we use sub-wavelength resonators or antennas on the surface. So what is realization means? How to get a surface with phase gradient phase. So you use sub-wavelength resonators or antennas on the surface with which are suitably designed geometries for scattering the electromagnetic wave in the desired phase distribution. What we require is we have to achieve a broad range of 0 to 2 pi phase shift at the interface. We have to use deep subwavelength thickness, subwavelength separation between them, and we must ensure high and uniform scattering amplitudes. Next. This is showing an antenna in which we are doing this. Look at the scattering intensity. Scattering intensity is around 1 over a small wavelength range. So that is the wavelength that we use. Phase gradient, you can see the phase gradient is from plus pi to minus pi, or minus pi by 2 to plus pi by 2. That phase gradient is there. Next. Now this explains the working of that antenna. In this, look at the electric field. Incident field is in the black. It has two components: the symmetric component ES, which is in blue line, and asymmetric component EA, which is in the red line. So when the symmetric component is exciting the antenna, V antenna, So the direction is along the direction of the arms of the V antenna. So the length is, if the total length is 2L, then each arm length is L. So ES is exciting 2 pi by lambda, sorry, lambda by 2 is equal to L. So it corresponds to that frequency. In the asymmetric mode, it is along the antenna whole length. So lambda by 2 is equal to 2L. So it excites that frequency. So we have two frequencies excited by the same antenna for one incident. So, right. So output will be the combination of the field from the symmetric mode plus the asymmetric mode. So E output is AS e to the power j Vs plus A is for asymmetric e to the power j Va. Similarly, if we take its mirror structure, mirror image, then mirror image means it is reflected by 180 degree. So 180 degree phase change. If there is a 180 degree phase change, same principle, same thing happens. Only thing is phase is changing by pi. So E out is amplitude remains change, phase change is pi. Arrange this along a straight line. So the bottom one, the yellow lines, they show the arrangement 0 pi by 4, 2 pi by 4, 3 pi by 4, then the mirror reflection of 0 pi by 4, 2 pi by 4, 3 pi by 4. So those will be pi or 4 pi by 4, 5 pi by 4, 6 pi by 4, 7 pi by 4. So this way we ensure uniform amplitude and 2 pi coverage. This was given by Yu and his group, published in 2011 in A Science. Next. Using this, we can generate a flat lens. Principle is this is the most conventional component that we rely on the, and this relies on gradual phase accumulation through the dielectric media. This shows you a lens, normal lens. You are incidenting some light, and those are having corpus, and when it passes through the lens, this becomes straight lines. Next wavefront becomes straight lines. The thickness is about the lambda or thicker of the lens. Now the question is, can we make it thinner? How to make it flat? The answer lies in this, that follow the same principle, Huygens principle that we followed. So that way you can engineer the secondary wavelengths using making it thinner. Next. Now let us consider the theory of the flat lens. For the flat lens, as we saw, it is going out in the straight lines. So theta t is equal to 0. Transmitted angle will be 0. Theta t has to be 0. Next. So sin theta t minus sin theta I is equal to dou x PR by K0. Nt is equal to Ni is equal to 1. It is the same medium of free space. So put theta t is equal to 0. This gives you minus sin theta I is equal to dou x PR 1 by K0 into dou x PR. Next. So from that we can find out what is d phi, that is minus K0 sin theta I dx. Then theta I we can find out from the top figure, that will be tan inverse R by F. F is the focal length. Then dx is equal to F by cos square theta I d theta I. Then find out what is d phi. For the dx, put this value F by cos square theta I d theta I in the d phi equation. So d phi is equal to minus K0 sin theta I F by cos square theta I d theta I. Next. So from that, we have to find out what is phi theta. So find out phi. Phi as a function of theta. Integrate both sides. So phi theta is equal to phi 0 plus integration 0 to theta minus K0 sin theta I into F by cos square theta I d theta I. Now integrate this. By integrating this, you will get phi 0 plus K0 F into minus cos theta inverse 0 to theta limit within the limit, that is phi 0 minus K0 F by cos theta minus F. So this is the design principle of a flat lens. Next. Then finally we'll come to beam shaping or shaping the ray direction, controlling the ray direction. Suppose we have a lens that we are trying to use for shaping the beam. So onto the lens we are incidenting rays for using a horn antenna. So we have a feed horn, and from the feed horn, electromagnetic wave is incident onto the lens, and from the lens it will go in the desired direction. So this R in the top, the R shows you the beam shape. In that shape, the beam must go out, and the R dash shows you the total beam shape. This R is the maximum energy, and R dash is the total energy. So on its side, the spillage on 1 and 3 is shown by R dash. Next. So again, here we use KR. First, we find out the expression for KR. Next, then KT expression. This is not the now it becomes the complete expression for KT. Now, from these two equations, we understand that delta or del of delta phi r or T is not uniform. That is not uniform in both these cases. So that we know. Now we have to determine the phase shift. Next. So gradient of phase shift is given by delta del of delta phi t is equal to kt minus this equation that we know already from kt equation. Similarly, dox phi r is equal to k0 sin theta t minus sin theta. These two equations we know from the reflection and the transmission equations of generalized sense law, three dimensional. Then, by for integration of phase shift, we find out phi xn is equal to phi at x is equal to 0 plus integration 0 to x and dou x phi r dx. If we do that integration, phi at x is equal to 0 plus integration 0 to x k0 dou and dou x phi r for dou x phi r. Put that expression k0 sin theta t minus sin theta I dx, then that integration will give you this expression. So integration of the phase shift. So what phase shift is required is given by this. Next. Then from that you will get different phase shifts. Take the minimum value of the phase shifts as the reference. So phi dash xn is equal to phi xn minus minimum of phi xn. If you put it in the algorithmic form, next. Then we see this algorithm start with the primary beam and the desired beam, put them together. Then from the primary beam, find out what is f theta and t. For the desired beam, similarly find out what is f dash and t dash. Then, and once we know this, then find out what is delta theta, which is theta max by n, and when n is equal to 1, small n is equal to 1. Capital N you get from n is equal to 1, 2, 3, 4 up to capital N. So capital N is the maximum number of phase elements. So n is equal to 1. Then theta 1 is equal to 0, theta 1 dash is equal to 0. This is the initial condition. From that initial condition, find out what will be theta n plus 1 and theta dash n plus 1. So using this, theta n plus delta theta, theta dash n plus delta theta dash n. Now, look at whether you have reached n is equal to n plus 1. If you have reached n is equal to n plus 1, that is, you are incrementing small n. If you have reached n is equal to n plus 1, then you stop, take the output as theta n and theta dash n. If you have not, then keep on incrementing n as n plus 1. So this is the beam shaping algorithm. With that, we come to the end of this discussion. I appreciate your patience. You stayed here. Thank you. If you have any questions, I'll be happy to try to answer that question.
Thank you, sir. Now it's open for questions and discussion. So I request all the participants, if you have any, I'm sure this deliberation must clarify so many doubts. However, you have any doubts, you can interact with the sir. Murtunjay sir,
Yes, sir.
yes, sir, the participant, they can unmute themselves.
Yes, yes, yes.
Okay, okay,
Participant can unmute themselves.
okay. Dear participants, you can ask if you have any query or any interaction with Mr. Sir.
Hello.
Yes, Devanshi sir.
Uh, Hello, Ravindra sir. Namaskar.
Namaskar.
Sir, it was a very nice, from the basic you have started and you have gone to the derivation in details of, about this meta surfaces and metamaterials. Just I have, sir, a simple question.
Yes, yes. Yeah.
Sir, you have told about this Pendry's perfect lens.
Yes,
Is it perfect lens? Is it
yes.
really possible or it's only theoretical, sir?
Um, you can say it is 99% viable. 1% problem will be there because of the loss. Because we are using metals for these structures. So those metallic loss will be there. This uh, resistive loss, because of the metal, there will be resistance. There will be some resistive loss. Beyond that, it is 100% possible. So you can say 99% possible. What we call superlens. Superlensing. Actually, in the optical domain, now they are using it. This has been realized. Microscopes have come with superlensing.
Okay, sir. Thank you.
Thank you.
Anyone?
Uh,
Yes.
Sir, namaste, sir.
Namaste.
Sir, a simple question, sir. As you change the transformation coordinate from XYZ to UVW, so any other properties are that changes, sir, due to the change of the refractive index and the epsilon? Uh, any other property that changes, sir?
No, no. Only the refractive index will change, or that is refractive index will change, which means only the permittivity and permeability will change.
Acha, sir.
That much change will be there. There is no other change except the loss. As I told you, because we realize this using metals, so there will be metal loss or resistive loss.
So
So that
reflectance and transmittance will also changes, no, sir?
small changes will be there because of the loss in the metal. That change will be there.
Yes. Okay, sir. Thank you. Thank you, sir.
Thank you.
Nitin sir, do you want to interact with Mr. Sir? Okay. Any other participants? Any more questions? Sir, I think they may have no more. There is no more questions. Deepak sir, are you there? Deepak sir.
Yes, Narayan sir.
Okay. Now I request Deepak sir to give a vote of thanks, because again tomorrow sir will take another session at 2 p.m. Then the participant may interact, and they may put more queries. Okay. Now
Have you
Deepak sir, over to
distributed?
you.
I don't know.
Sir,
Have you distributed the course material? Course material I have supplied. Have you
sir,
distributed?
sir. ନାଇଁ ସାର୍ ସାର୍ ସେୟାର କରିନାହାନ୍ତି, ଆପଣ ବୋଧେ
Yes,
ମିଟିଂ ଦେଇଛନ୍ତି।
yes. Now, sir has shared, so it will be. Sir has sent to my mail, so it will be shared after the lecture. Yes.
Okay. So then they can come prepared, and that will be more
Yes sir,
interactive.
it will be interactive. So that we request you go through the material that we will share after this talk, then be prepared, and hope it will be interactive in the next session. Deepak sir, over to you.
Thank you, Narayan sir. So, very good afternoon, all. So, it was a very wonderful session, starting from basic fundamental of materials to meta surface. It was really illustrative talk, but it was completely, I can say that it was mathematical. So, most of these participants may not have captured all the things, but I hope in the next session it will be more interactive. So again, thank you, Mr. Sir, uh, for receiving our agreeing with us to give a lecture on uh, meta material or meta surfaces. So I hope it will be helpful to not only the participant or research scholar teachers, but also as a host, we are also very exciting about all these topics that uh, is going to be delivered by all the dignitaries. So thank you, Mr. Sir. So we hope it will be more interactive in the next session. So again, thank you, participants, for joining us in holiday also. So that is more important that in Sunday also all the participants join in timely. So thank you all.
Thank you.
Sir, Mr. Sir, sir
Ah,
ମୁଁ
Narayan.
ଦୀପକ ସାର୍ଙ୍କୁ କହିଛି ଆପଣଙ୍କ ଟକ୍ କୁ ବେସ୍ କରିକି ଆଜି ଆଉ କାଲି ମିଶେଇକି 4 କି 5ଟି ଆସାଇନମେଣ୍ଟ ସେ ତିଆରି କରିଦେବେ, ଆମେ ପିଲାମାନଙ୍କୁ ଆସାଇନମେଣ୍ଟ ଦେଇଦେବୁ।
ଦେଇଛି କ୍ୱେଶ୍ଚିନ୍ ଦେଇଛି,
ଆପଣ ସାର୍ ଦେଇଛନ୍ତି?
MCQ ଦେଇଛି, ସବୁ ଦେଇଛି।
ହଁ ସାର୍, ଠିକ ଅଛି ସାର୍।
Multiple
Sir,
choice.
MCQs for the test only, which will be conducted at the